Today we get to start a new unit on the applications of integration. And the first thing we'll start with is talking about straight line motion again. Kind of like what we did first semester, we'll bring in back some of those topics and talk about how we can apply integrals to these topics. In first semester, when we looked at straight line motion, we always were looking at the derivatives. So the derivative of position was velocity, the derivative of velocity was acceleration, and we were able to apply derivatives to straight line motion in that sense. In this section, we're going to go in the opposite direction. So given maybe some of these derivatives and or second derivatives, we're able to go back to the original functions that they came from, given some initial information or initial conditions about them. So for example, here's this formula right here. It says, in order to find a velocity function, if you're given an acceleration function, all you have to do is take the integral of the acceleration function, and it puts you back at the velocity function with this constant of integration that we can answer. So here's some examples of how we can do that. It says, find the velocity function given the acceleration function and information about the velocity function when it's equal to 0. So first things first, we can take the integral of both of these. The integral of the acceleration function, dt, is going to be equal to the integral of 4t minus 6 dt. So if we integrate both sides of this equation, that will allow us to find the velocity function. The integral of a of t, the integral of the acceleration, is velocity. The integral of 4t is 4t squared over 2. The integral of 6 is 6t, and then we'll put plus c. Excuse me. If I simplify this a little bit, I get 2t squared minus 6t plus c. So this is a general equation for the velocity. If we want to find out the specific equation for the velocity function that this acceleration function came from, we would plug in 0 for t and 3 for velocity. That's called an initial condition. So in this equation, everywhere I see a t, I'm going to plug in 0. Everywhere I see v of t, the velocity, I'll plug in 3. So this is 3 equals 2 times 0 squared minus 6 times 0 plus c. Therefore, 3 is equal to c. So my constant of integration is 3. If I write my final answer, that would be the velocity function that we found out, but no longer do I need to write it as a general solution. I can now write it as a specific solution. So 2t squared minus 6t plus 3. There's the exact velocity function that gave me this acceleration function as its derivative. On example 2, if we integrate a of t dt, and we integrate sine of t plus 2t dt, we get that the integral of a of t is v of t. The integral of sine is negative cosine t. And the integral of 2t is 2t squared over 2. I hope it's okay with you guys now that we're kind of a little bit more into integrals if we start to simplify these things immediately. So if I integrate this, it's 2t squared over 2, which would simplify to just t squared plus c. If I plug in my initial condition at 0, at t equals 0, the velocity should be equal to 5. So 5 equals negative cosine of 0 plus 0 squared plus c. Cosine of 0 is equal to 1, so this is negative 1 plus c is equal to 5. Therefore, c is equal to 6. And my specific solution for this function is now v of t equals negative cosine of t plus t squared plus 6. So that's how we will solve for velocity given acceleration, is just by taking the integral and using the initial condition to figure out what the constant of integration is. We can also do that, by the way, with velocity and position. So if I was given a velocity function, if I took the integral of that velocity function, I would get a general position function. And if I was given an initial condition about the position, I could plug it in the same way we did these to find out the specific position function. All right, some terms you may be familiar with, but let's talk about them a little bit more in depth and how they apply to us in calculus. These two terms, distance and displacement. Again, most of you guys are probably already pretty familiar with these, but we'll talk about them a little bit more in depth here. The distance is how far you travel between 2 points in time, which includes when you go in positive directions or negative directions. And you don't want those two directions to cancel out your distance. So you have to take into consideration all the times you turn around and change direction so that you can add together all of your distances rather than having the positives and negatives cancel each other out. Displacement, on the other hand, is just the difference between where you start and where you stop. So if you go forwards and then backwards and then forwards and then backwards, all of those would add and subtract from each other. And I just want to know how far am I away from where I started. So here's a little image to help us see this. If we start here and we travel 80 miles to the right and then we decide to turn around and travel 60 miles to the left and stop here, my displacement is only 20 miles because if I move 80 miles one way and 60 miles back the other way, I've only really gained 20 miles in that. But my distance, if you add together both of them, would be 80 plus 60. So without direction, I just want to know how far I went. So 80 plus 60 would be 140 miles. Question down here says, can distance ever equal displacement and how? The answer is yes, if you never turn around. If you only go in one direction, then your distance and your displacement would be equal to each other. So a couple formulas that we are needing to know, so I definitely want you guys to write these down. I'm actually going to add one more to this as well. It says if we're given the velocity function, which we know is always positive, then they would be equal, distance and displacement. But like we've said, that's not always the case. So it's our job to differentiate between the two and to try to figure out how to account for the fact that we could be going in multiple directions. So these two equations, make sure you write down. It says, given a particle moving on a straight line with a velocity function between time equals a and b, displacement would just be the integral of the velocity. So to figure out how far you are from where you started, if you just integrate the velocity, that would add together all of the area under the curves. So no matter positive or negative, they would just start canceling each other out, and we would have the displacement. But if you want the distance, we have to look at the absolute value underneath the curve, because I don't want the negative areas canceling out the positive areas. And so typically these problems would occur in a calculator. It's not very often on the AP test that they ask you to do a problem like this by hand, where you actually have to find the positive intervals and find the negative intervals and account for the negative ones by making them positive. So on the AP test, when they're asking you for that, you would just throw absolute value bars around your velocity function to account for that. And then the one I wanted to add that's not in here is actually position. And actually, I'm going to write it over here. So position is it's the displacement essentially, like how far are you away from where you started, but then adding in your initial condition. So it's your initial condition plus the displacement. So if I started like 5 miles north of Ontario or something, and then I traveled 15 more miles north of Ontario, my displacement is 15, but my initial condition plus the displacement would be 5 plus 15, which would be 20 miles north of Ontario. So that's another thing I want you guys to make sure you're aware of. Let's do an example. It says a particle is moving along a straight line with the velocity function equal to t squared minus 7t plus 10. Find the displacement and the distance traveled on the time interval from 1 to 7. Notice that I can't find the position necessarily just because they didn't tell me where it started. So if I don't know where it started, that means I don't have an initial condition and I can't find its exact position. So displacement is the easy one. Displacement is the one where we just find the integral of this velocity function. So the integral of t squared minus 7t plus 10 dt. And my limits of integration, I want to know how far it traveled between 1 second and 7 seconds. So the integral of t squared is t cubed over 3. The integral of negative 7t is negative 7t squared over 2. The integral of 10 is plus 10t. And again, because we are evaluating over a specific interval, we don't need the constant of integration. We just need our limits of integration. If I plug in 7, I get 7 cubed over 3 minus 7 times 7 squared over 2 plus 10 times 7 minus, if I plug in 1, I just get 1 cubed over 3, which is 1/3, minus 7 over 2 if I plug in 1 plus 10. Now, I am totally fine with you guys using a calculator to do this problem. I don't necessarily need you guys to do it by hand. Your answer could be a decimal, your answer could be a fraction, it's up to you. So if I do this on my calculator, I get 7 cubed divided by 3 minus 7 squared times 7 would be 49 times 7 over 2 divided by 2 plus 10 times 7 would be 70, and then minus 1/3 minus 7 halves plus 10. And I got that to be 6. So the displacement, the difference between where this particle started and where it ended up, was 6 feet. Now the distance, which is the more difficult one, is the fact that you have to account for where it's positive versus where it's negative. So if I look at this velocity function, t squared minus 7t plus 10, if I can try to find out where it's positive versus negative, I have to first know where it's equal to 0. So this factors to t minus 5, t minus 2, which gives me t values of 5 and 2. So I know it changed direction at those 2 points. I guess I don't need that much graph. So here's 5, here's 2, and I know my equation looks something like that. So it's positive when it's less than 2, and it's positive when it's greater than 5, but in between 2 and 5, it's negative. So if I want to not have that negative area canceling out with my positive area, then I need to look at the absolute value of this function, which would look like this red one that I just drew. So essentially, I'm going to add together the areas under the curve by taking the integrals, but as I do that, this one gets to stay positive since it's already above the x-axis. This one gets to stay positive since it's already above the x-axis, but this one in the middle, I need to make a negative so that it flips up top above the x-axis. So my integral actually looks like this. It's the integral from, 1? We're starting at 1, right? Yeah, at 1. So it's the integral from 1 to 2 of this velocity function, plus the integral from, minus the integral from 2 to 5 of this velocity function, plus the integral from 5 to 7 of this velocity function. Now, the reason that these two first and last ones are positive again is because they're already above the x-axis. This middle one is a negative area, so if I want it to turn positive, I have to make it another negative, because a negative area will turn into a positive area. Now, I won't make you guys do this by hand. It would require a lot of work in the sense of integrating this, which we've already done, but using the fundamental theorem of calculus 3 times, from 1 to 2, from 2 to 5, and from 5 to 7. So I actually want you guys to try and practice this in your calculators, see if you guys can figure it out in your calculators. So I'm going to go ahead and kind of walk you through it verbally, and then hopefully you guys are able to figure it out. There was a video in the last unit about how to do this, so hopefully you guys watched that video and you know how to do this, and I'll just kind of walk you through it verbally. So first things first is you want to enter in your y equals into your function. So for y1, we'll put in t squared minus 7t plus 10, squared minus 7t plus 10, and I'll put it in terms of x. Then we can go back to the home screen. Once you have that in the home screen, remember that to pull up a definite integral, you go to Math 9, and then fill in all the information. So fill in the lower limit of integration and the upper limit of integration, recall the y1 function to put it in, and then the important variable is x. So do this 3 times. Do it from 1 to 2, from 2 to 5, and then from 5 to 7. Write down your answers those 3 separate times, and then plug them in this formula. So add together the first ones and the last ones, and then subtract the middle one. So I'm going to go ahead and do that right now, and then I'll put the work up on the screen in just a second. Alright, so I put each one in my calculator individually. The integral from 1 to 2, I got 1.833. The integral from 2 to 5, I got negative 4.5, so I subtracted that, made it a double negative to make it positive. And then the integral from 5 to 7, I got 8.667. If I add all 3 of those together, I get 15 feet, so it ended up being a distance of 15 feet. You'd notice, by the way, that if you added this and didn't make this a negative, if you kept this a positive, that these 3 numbers should have added back to 6 again to show the displacement if you never accounted to make this positive. Perfect. Again, typically on the AP test, they don't ask you to do it like this, where they ask you to break up the intervals that are positive and negative. typically they would just have you put it in your calculator. So in your calculator, you would essentially just type it in like this. You would type in what's the integral from 1 to 7 of the velocity function of this function, but you would just throw absolute value bars around it. Try it now in your calculator. Make sure you get 15. To recall the absolute value bars, by the way, you can either go to math, number, if you scroll over to NUM for number, and then the first option is ABS for absolute value. You can recall it that way. I think there's another way if you go to like alpha F2 or maybe alpha F3. I'm not quite sure. I don't have my yellow calculator with me right now. But if you go to one of those two options, I think that's another way of recalling the absolute value function if you want to do it that way. All right, just visuals, by the way, to show you what it looks like for that last graph. For the displacement, we were just finding the area under the curve for this function. So positive area, here was a negative area, and here's another positive area. Versus here, when you throw absolute value bars around it, now all of the areas are positive, so they're just adding together. But again, that's how you would do it. Last example of this lesson, it says a car is 15 miles north of Ontario. It begins to drive, and its velocity is modeled by the function v of t equals t squared minus 5t plus 6. Compare the displacement, the total distance traveled, and the position of the vehicle after 5 seconds. So, displacement. Remember, that's the easy one. Displacement would be the integral of t squared minus 5t plus 6 dt from we'll say time equals 0 when it started to 5 seconds. Now, even though it is good practice to do this by hand, a lot of times these problems are in the calculator section. So I want you guys to actually get your calculators out, and I want you to see if you can do that in your calculator. So I'll do it with you right now. Because we're going to be recalling this function multiple times, I'm going to put in my y equals. So I'm going to go to y equals, I'm going to type in x squared minus 5x plus 6. And then I'm going to go back to my main screen. After I do that, I'm going to recall the integral function. So remember, that's math 9. And then you're going to insert your limits of integration. So insert 0, insert 5, and then recall that y1 function, dx in this case. So I will do that now for mine. Function y1. And I got that the displacement is equal to 9.167. It doesn't have... Oh, I guess that shouldn't be 5 seconds. That should probably be a different time. That's okay. I guess this car is going to be driving really fast. We'll just put miles per second. Oh my gosh. So since it's displacement, just miles though. Miles. There we go. So this is like the speed of light car. Probably this should have said 5 minutes or something like that. But that's okay. All right, displacement. That's that. Distance. So for distance, it's the same integral, 0 to 5, but this time instead of just putting the function in, I want you to put absolute value bars around it. So in your calculator, again, I want you to go into Math 9, insert absolute value bars, so whether or not you want to do it from alpha, f, whatever, or if you want to go to math, number, absolute value, it's up to you. And then insert the function inside of that. And then ask it to take the integral from 0 to 5 again. When I did that, I got... It takes a little bit longer, by the way, to do the absolute value. Your calculator has to think a little bit harder, because it's actually calculating those points where it equals 0 and figuring out where it's negative versus positive. I got 9.499, so 9.499, I'll just truncate and cut it off right there. You could have rounded it up to 9.500. All right, so we went backwards a little bit, not too bad. And then for position. Remember that position is the displacement plus the initial condition. So if my initial condition is that I started 15 miles north of Ontario, that would be 15 miles north of Ontario plus when I started to when I ended my displacement, t squared minus 5t plus 6 dt. And we already calculated the displacement. We know that the displacement is 9.167. So if I add how far I went plus where I started, that would be 15 plus 9.167, which gives me 24.167 miles. This one should have been miles too. Miles north of Ontario. So again, this is a super, super speedy car. It was able to travel 9 miles in 5 seconds, but that's okay. It doesn't have to make a ton of sense. But that's how you find displacement, distance, and position. These are very, 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 very heavily weighted. Maybe not as much as function analysis, but these questions come up often and students get confused by them often. So make sure that you know the difference between these three equations. Displacement is just the integral. I want to know where distance from where it started to where it ended. Distance throws the absolute value bars around there. So don't give me any negative intervals. Make everything positive so that I can figure out how far I went in total. And then position takes the displacement, distance from where you started and where you ended, and then just adds in where you started to figure out where you are now, essentially. All right, and that's all for today.